In this video, I want to introduce you to the Poisson distribution. Now, the Poisson distribution can be used to describe a number of real-world scenarios. So I've just written up a few. So, for example, the number of cars passing over a toll bridge in a minute, the number of radioactive atoms that decay in an hour, or the number of misprints that will occur on a page in a book. So all of these are examples of rates. So you've got something happening within either a certain time frame or in a certain area. Okay, so the rate, the average rate at which these things happen, we label as lambda. So we use the Greek letter lambda to represent that. And we write that x is a Poisson distribution, so PO, with this one parameter lambda. Okay, so as I said, lambda is the average rate that happens over a fixed interval of time. So it might be a minute or an hour or a day or a month. Or it could represent a space. So it could be a page on a book, or it could be a square meter area, for example, or a mile radius or something like that. Okay, so with that, you then have its distribution itself. So the probability of x being equal to r. Now the formula for this will look a little odd. Okay, probably not what you are expecting, but it starts off with e to the minus lambda. Now e here is the number e that you should have met at this point, so 2.71, etc., the irrational number e, and that's multiplied by lambda to the power of r over r factorial. It's quite a strange looking formula, but you will need to know how to use it. The actual formula is given to you in the formula booklet, and it takes on the values, so that r takes on the values from 0, 1, 2, 3, 4, 5, 6, 7, etc. forever. So it's unbounded. Okay? So unlike the binomial distribution where it is capped at a fixed number of trials, the Poisson distribution is not. Okay? Now, a couple of other things about the distribution itself. We also have E of x and var of x. So while this is given to you in the formula booklet, E of x and var of x aren't. It turns out that E of x, the expected value of x, is just lambda, the average rate, which probably isn't of great surprise, but it is something that we can prove, and we will in the next video. Okay, but that is an extension video, so you won't expect you don't expect to be able to prove it in the exam. But E of x is equal to lambda, and var of x is also lambda. And again, we prove that in a coming video. This is given to you in the formula booklet. As I said, this is not. You're expected to know that. Okay? And one thing that you can use to tell if a distribution is likely to be Poisson or not is if you calculate E of x and var of x, and you find that they are both very close to one another, then that is a good indicator as to whether a Poisson distribution is appropriate. Okay? So if you've got something like E of x is 3.25 and var of x is 3.29, they're reasonably close. Okay? So it may well be that a Poisson distribution would be appropriate. Now, you do need to know that there are three things that you should look out for, okay, with a Poisson distribution. You need to know the facts of when a Poisson distribution is appropriate to be used. Okay, so there are three that you need to know. The first one is that the events must occur independently and randomly. Okay, so the events occur randomly, okay, and are all independent of one another. So do the events occur randomly and independently? So it may well be that you're given a scenario and you've got to describe whether you think it is Poisson or not, whether a Poisson model would be appropriate. If you don't think the events occur randomly or they're not independent of one another, then that is something you need to explain. The next thing you need to know is that for a Poisson distribution to be the case, you must have that the events occur singly. So the events happen singly. Now, what we mean by that is one at a time. So you can't have 2 or 3 happening at the same time. And finally, the events happen on average at a constant rate. And that's your lambda. Okay, so you must have this constant rate lambda in order for it to be a Poisson distribution. Okay, so what we're going to see in the next couple of videos is deriving these 2 results. Okay, as I said, they are extension videos, so you won't need to replicate those in the exam, but they're there for interest's sake. Then we're going to get into the thick of being able to calculate probabilities and finding out more of the properties of the Poisson distribution as we go.